Let's start the introduction. All right, welcome to the DDPS seminar, everyone. Before we introduce our speaker today, let's go over some rules and logistics. First of all, please mute yourself during the talk, but if you have questions, you can unmute and ask questions, or use chat room to post your questions so that we can address them in Q&A session at the end. Second, today's DDPS seminar is open to external audience. Therefore, no classified discussion is allowed, so please watch out. Finally, the talk today will be recorded and uploaded in our YouTube channel. Okay, let me now briefly introduce our speaker today. It is an honor to host Dr. Fabio Giampaolo, who is a research fellow in computer science and artificial intelligence and a member of the Modal Research Group at the University of Naples, Federico, where he received his PhD in the mathematics and applications. Member of the editorial board of the journal Neural Computing and Applications, and he published by Springer, and he has co-authored articles in international journals and conference papers on both applicative and methodological research in the deep learning field. His research interests include machine learning and deep learning, with a particular focus on exploring the dynamics of learning. This explorations encompasses a wide range of topics, including the development of innovative neural network architectures, the investigation on new learning algorithms efficiency, and the application of these methodologies to solve complex real-world problems. Today, Dr. Giampaolo will talk about learning paradigms for neural networks and the locally backpropagated forward-forward algorithms. Please enjoy and expect a wonderful talk from him. Now let me ask questions to our speaker, just to make this stage somewhat informal. Is it okay to ask a question?
Course.
All right, yeah. Awesome. So we usually do that. Okay, obviously you're passionate about the deep learning or neural network. Would you share with us the moment when you realized that you want to dive into this community or neural network?
Yeah, this is a good question. I was one of those kids that was always in front of his computer, trying to code and something like that. So when I found out that in the department there was a research group dealing with this kind of topics, and in particular on how machine can learn, I was very fascinated by this. So I asked them to work with them. I started to work with them, and so that's why I ended up where I am now.
Awesome. Well, these days you probably are more fascinated by what they can do. All right, the stage is yours.
Okay, I will share my presentation. So
full screen.
Can you see the presentation by now? Yeah.
Yeah, but it's not full screen.
Okay.
If you can make it full screen.
Is it now?
Yeah, it is.
Okay.
Thank you.
So I will start. Of course, good morning, everyone. First of all, I would like to thank again Young-Soo and the organizers for giving me the opportunity to hold this seminar. As Young-Soo said, I'm Fabio Giampaolo, a research fellow at the University of Naples, Federico II, and a member of the Modal Research Group. This is a brief outline on what we are going to discuss today. We will start by introducing briefly some basic concepts on neural networks, the way a neural network is tailored to a specific task, and some fundamental concepts around the learning process. Then we will move on to some manipulation, some experiments about the manipulation of the learning dynamics, and we will end the presentation by discussing some applications of the main ideas we developed in the field of federated learning. I think the audience is familiar with the concepts shown here, so I will just introduce them very, very briefly. We know that the neuron is the foundational computational unit on which all the neural networks are built. And we also know that it can be seen as a two-step process. First, the input undergo a weighted sum, to which is also added another term, bias. And then the result of this sum is processed through a usually nonlinear transformation, here denoted as lambda, which is the activation function. So a deep network can be seen as a stack of strata, the layers in which the neurons are arrayed. And from a general perspective, it can be imagined as composed by three main segments. No? The input layer, which ingests data, the hidden layers that work together to extract complex patterns from data and to provide a functional representation for these patterns. And then the output data that provides the output that aligns with the task we are dealing with. It should be underlined that some theoretical results exist about this kind of structures, as in particular about the approximation power of this kind of structures, as in particular demonstrated by the universal approximation theorems. Usually these results concern the approximation capabilities of a feed-forward neural network on the space of the continuous functions, and the approximation is with respect to the compact convergence topology. However, despite the importance results like this one have from a mathematical perspective in the formulation of a neural network, they come with a major concern somehow. They do not provide a construction rule for the weights, for the synapses, for the connections of these networks. So in this scenario, we may say that the deep learning problem, the learning problem, can be seen as the problem of learning the connection weights of a large computational graph. But in order to address this task, we must introduce another basic yet fundamental concept in the learning framework, which is the loss function. This function basically measures the discrepancy between the model's predictions and the target values, and can be formalized as reported here. It's worth noticing that we may say that the loss function somehow encapsulates the objective of the task by measuring the model's deviations from this objective. And in this slide, I reported the general formulation for a loss function with also some desired properties, which are actually not always fulfilled. And with the concept of loss function, we can reframe the learning problem as an optimization problem, no? Which deals with the loss function. In this framework, our task is to find a set of weights that minimizes the loss function. So considering a network made up of n units, we should find a learning rule somehow, no? A way to adjust weights in such a way this condition is fulfilled, the condition reported, the partial derivative of the loss function with respect to the variations, the variation of all the weights in any critical point. It is peculiar to notice that even if the research on this topic has been huge somehow, only few algorithms have been proposed to do that. And with reference to the table, we may also notice that all the familiar learning rules we are used to somehow can be seen as special cases or variations of the two main learning rules, which are the Hebbian one and the backpropagation one, which are different in their essence. However, in this framework, another important question arises, and that is to say, what characteristics should learning rules have to guarantee an efficient learning process? Following what we said, we should require that learning rules depend on variables that are locally available, as shown here. For example, on variables that could be the presynaptic activity, the postsynaptic activity, and the weights itself. Then we must notice here that the targets will be considered local only for the output layer of the network. And if we stop here, we obtain what we call the deep local learning, which occurs basically by applying these two learning rules layer by layer from the input one to the output one. However, it can be demonstrated that in this framework for a network it is impossible to learn optimally a complex function. And in order to address this, we must require that some sort of information is propagated from the targets to the internal weights of the architecture. And this is what happens in what we call local deep learning, in which the generic learning rule is modified by adding the dependence of some sort of information that traverses the network and arrives to the deep weight. Moreover, we can also require that this information comes in a simplified version somehow, for example, depending only on the postsynaptic activities. And in this case, we can obtain a formulation for the learning rule as reported in equation 3, which can be proven to be equivalent to a local supervised rule in which the targets is directly delivered to the weight. And why is this important? Because backpropagation, for example, works just like that. So let's for a moment focus on the backpropagation. I think that also this process is well known here, but I will discuss it very, very, very briefly. We know that the backpropagation is the standard way a neural network is trained, basically, and it can be imagined as a two-step process, two-pass process somehow. In the forward pass, as the information crosses the layers, it is transformed by all the weights and the activation functions of each computational unit. And in this way, the model is able to produce a prediction that can be compared with the expected target value, so we can measure a distance between these two quantities. In the backward pass, the information about this error is propagated backwards through the network by applying the chain rule of calculus to the composite function of the loss and all the operations performed by the layers of the network. And this is reported in these three equations, basically, in which we can see how the error computed on the last layer of the network is transmitted to the generic internal weight by the recurrence pattern, which is obtained by applying the chain rule to the generic feed-forward formulation. And in the whole training process, these two steps are iteratively performed until we reach a minimum for the loss function, or usually until we met a stopping criteria. We can also reconnect the backpropagation with the concept of local deep learning by considering a learning rule in a multiplicative form in which appears the target. Now, recalling what is the learning rule for the backpropagation, which is basically the equation 6 here, through some straightforward manipulations, we can obtain a formulation for this target t in terms of the backpropagated error. And notice that here we use the simplified form of information I of I, since backpropagation shows that it is possible actually to deliver the same information to all the synapses connected to impinging to the same neuron. In this context, we can also write down a general formulation for this learning rule, with backpropagation being a special case, in which we can notice that the information depends on the targets, on the output, and on all the upper layers of the network and all the upper derivatives. By the way, there is a reason why the backpropagation is so efficient and then so widely used. If we perform a Taylor expansion of the error function around the generic weight and also considering the mole fluctuation delta W, we can somehow estimate the effectiveness of the information transmitted to the deep weights. To first order approximation, we can see that the information that is sent back to the deep weights can be interpreted in terms of how well it approximates the gradient G. And since the most of information of the gradient is contained in its direction, the estimation of what here we call the O returns a measure, more or less, of how good is the corresponding optimization step. Together with gradient information, we can also estimate some other quantities which basically deal with the efficiency of the transmission of this information. A very interesting discussion about this topic is in a work of Baldi and Sadowski, from which also this figure is taken. And they demonstrate basically that in this framework, backpropagation is optimal, since it achieves both the maximal possible rate of information and the maximal possible improvement. Now, despite the optimality of backpropagation and also its very efficient implementations from a computational point of view, the research in looking for alternatives to this learning algorithm has found more and more space in the community. And one of the main concern about backpropagation is its biological plausibility. There is no convincing evidence that biological networks explicitly propagate gradient error information or store neural activities for the subsequent use in a backward pass, or again, the requirement for such a strict symmetry of the weights across the learning seems particularly implausible. So these considerations, with also others briefly reported here, have pushed the research in this on this topic somehow. But also from a practical point of view, not only from a theoretical, philosophical somehow, if you want, point of view, backpropagation shows some drawbacks that limit its application, and in particular, the need for computing the gradient of the loss with respect to the whole composition of the layers functions may be difficult or even not possible in some cases. The most straightforward example reported here is the presence of a black box inside the model, inside the architecture, no? Unless we provide a differentiable model for this component, derivatives cannot be computed, and so we cannot apply backpropagation. In this case, of course, we may rely on different strategies, for example, reinforcement learning or evolutionary algorithm, but often these alternatives increase computational demands and are less efficient at scale. One may wonder when this limitation, when we are forced to face with this limitation in real cases. Here, I've reported just a few examples. For example, the integration of AI systems with legacy systems that not always, but often lack the interfaces for gradient-based learning, or real-time decision systems in which are involved the threshold-based classifiers or rule-based systems, or again, in techniques involving pruning sparsification, for example, as concerned the network architecture search. Here are involved the non-differentiable operations, usually like thresholding or masking, or probably in the most interesting context, which is the integration between AI systems and humans, in which here we must consider as inputs preferences or qualitative feedbacks which are inherently non-differentiable and which may make gradient computation a problem. Following some of these considerations, in particular the theoretical ones, driven by the implausibility of the backpropagation, in December 2022, Professor Geoffrey Hinton proposed an alternative learning procedure called the forward forward algorithm, which replaces basically the forward pass and backward pass of the backpropagation with two forward passes, one on positive data and the other one on negative data. And with positive and negative data, we're basically referring to actual data, real data, and wrong data. In this framework, each layer has its own objective function, whose aim could be simply described as having an high goodness for positive samples and a low goodness for negative one. And in particular, the objective of the task of the learning process is to achieve a goodness value which is significantly above a certain threshold, in this case, theta, for positive samples for real data, and significantly below that threshold for negative data. So, for example, in a classification example, in a classification context, the goal is to accurately classify an input vector as positive or negative, with the probability for an input vector being classified as positive given by applying the logistic function to the goodness value minus the threshold. And if we, moreover, can connect the goodness function with the neural activities, for example, through the norm, as reported here, we can write down the layer-wise loss function as reported as shown in equations 16, 17, and 18. It's interesting to notice that in this scenario, the weight update rule becomes in the form reported in the blue box, in which we can notice that the information I depends loses its dependence on the upper derivatives, and this somehow localizes the learning on the layer. But how does this learning process behave in the context of a supervised learning task? In this slide, I reported the behavior of the learning somehow in the case of a classification task involving the dataset MNIST. It's worth underlining that MNIST is very well known, and the behavior of simple networks trained through backpropagation on these datasets or datasets like MNIST are well studied in literature. So this makes MNIST very convenient for testing out new learning strategies to see if they actually work. However, in this context, for the forward algorithm, the classification is done by accumulating the goodness of all but the first layer for each label, and then taking the label with the highest accumulated goodness. Now, in general, we know that deep networks consist of multiple layers, and we can say that each layer processes its input and returns to the subsequent layer what it has extracted. And in a network trained by backpropagation, this allows for an increasingly complex representation of data, since the learning happens in a hierarchical manner somehow. No? For example, in this case, the MNIST case, we may see that first layers of the architecture will extract simpler features, for example, edges, and later layers of the same architecture will extract more complex features, for example, shapes. But and this hierarchical representation of data basically allows the network to build a robust representation for the data and to provide accurate predictions. In the case of the pure forward algorithm, instead, it could be said that each layer returns a measure of consistency between the sample and the target. And this can be seen from the figure I reported here, in which is shown the norm of the neural activities for all the layers with respect to the association between the sample 7 and all the possible targets from 0 to 9. And we can see that in this case, the learning somehow flows through the network since each layer receives no feedback on what's happening in the later parts of the structure, the neural structure. And this obviously impacts the overall convergence process. The figure on the left here reports the error provided by the layers 1, 2, 3, and the stack of the cumulative error provided by the stack, which goes from 1 to 3 as concerned the layers. In this case, we can see that, for example, layers 2 and 3 do not positively contribute to the prediction, since their marginal contribution is negative. Basically, the first layers provides a lower error with respect to the others. And the same thing can be seen also in the two figures on the right, in which are reported the accuracy of stack of layers of increasing dimension from 1 to 5, from 1 to 10, and from 1 to 15. And we can see that for the datasets MNIST and fashion MNIST in this case. And we can see that these three lines at some point separate, indicating that somehow each layer is less capable of the preceding layer to understand how to work with the input it is receiving. And this leads to two main considerations. The first is that a neural network trained with the pure forward algorithm struggles in learning collective representations. And from this follows the fact that the forward algorithm better performs with small networks, shallow networks, networks made by few layers. However, these new learning strategies has also some peculiarities we are interested in. For example, since the learning is somehow local, there is no need for the backpropagation in the weights update process. And this is interesting since it allows us, for example, to insert in a neural architecture a non-differentiable, a black box, a non-differentiable component without impacting the whole training procedure. Moreover, we know that each layer directly contributes to the prediction process. And this is also interesting if we think, for example, about the importance of ensemble methodologies in the field of machine learning. So with the idea of enhancing the efficacy of the forward algorithm, we developed a methodology whose basic idea is to split a neural network in blocks, then applying the backpropagation inside each block, but training each one of the blocks according to a forward-forward strategy. A small remark here involves the third consideration. Since no error information is propagated backwards, we can say that the first layer of the network somehow will be optimized sooner with respect to the other layers of the same architecture. But we will discuss this point in a few slides in order to make our approach even more efficient. Basically, sorry. Basically, the split strategy has been formalized as reported in this slide. We can say that the generic neural network can be partitioned in capital K non-overlapping subnetworks, and that the weight update process follows a backpropagation approach inside each subnetworks, where the error that is propagated backwards depends on the goodness function evaluated on the last layer of the block of the subnetwork. It's worth noticing that in this context, except for the first one of the blocks whose input is simply the data we have, for each one of the blocks, the input will be the output of the preceding block. So we are preserving the general feed-forward architecture. Now, in neural networks trained with backpropagation, we know that all the layers interact, collaborate to minimize the loss function. So we may say that each internal layer is loss function, which is computed on the last layer with the results of the last layer. So we may say that in a backpropagation process, each internal layer of the architecture is optimized in the sense of giving a good embedding to the subsequent layers. But this fact in our approach means that internal layers of the blocks will not contribute to the prediction process. And this is basically what we are seeing here from this figure, in which we can observe that while for layers 2, 4, 7, and 19, while these layers fulfill the condition, the goodness condition somehow, internal layers of the network do not know how to fulfill the prediction task. No. And given that, since we wanted to push on one side the layer interaction, but on the other side we wanted to preserve the layer-wise prediction contribution, we developed a randomized partitioning strategy, which basically consists in fixing the number of the blocks in which the network is split, but randomly varying at a fixed number of epochs, their sides, their extrema. And this guarantees that more or less during the training, all the layers will undergo the optimization criterion dictated by the goodness function, so preserving the characteristic we are interested in. And here we can observe how the random reorganization of the blocks impacts the learning pattern somehow, recovering the layer-wise prediction contribution. It can be seen from the last image here on the right. Of course, in this scenario, two main questions arise. If the interaction between layers is actually improved, and if we obtain a better convergence pattern of the entire network. And this second question arises from the consideration that now the layers are optimized also in the sense of giving a good embedding to the subsequent layers. So we expect a more coherent learning pattern across the whole network. And in particular, in this slide, we can observe that actually the random reorganization works somehow as expected. We can see that the three lines that I discussed before, now, for example, in the case of MNIST dataset collapse, but also in the case of fashion MNIST dataset, even if they still separate at some point, the pattern of convergence is much more coherent, is smoother somehow. And another thing that we can notice is that the overall accuracy is here in terms of error is improved. Of course, this proposed strategy introduces two other hyperparameters, that is to say the number of the blocks in which the network is split and the epochs for the random to wait until the random reorganization. Fixing this last parameter to 5, we can see on the left that actually reducing the number of the blocks stabilizes the convergence, while increasing the number of the blocks returns a convergence pattern, this time in terms of accuracy, much more similar to the pure forward-forward, which is the blue line. And this is explainable by the fact that if the network is fragmented, information about the layer interaction struggle in traversing the whole network. So we have a behavior like in the forward-forward algorithm. 10 blocks means 2 layers per block, basically. On the other side, we can see that increasing the frequency for the random reorganization stabilizes and accelerates the convergence in this case, while decreasing this frequency produces a slower convergence behavior. And this is explainable by the fact that if we fix a block for a considerable number of epochs, the backpropagation will saturate somehow the optimization of the last layer of the block in terms of goodness function, while not optimizing the internal layers of the block in this sense. So patterns just like, for example, this staircase appear, which is in the case of we are dealing with 25 epochs to wait until reorganization. And I would say this staircase pattern appear. By the way, in both the cases, we can observe that the overall convergence, overall accuracy is incremented. And this somehow shows that the presence of backpropagated blocks somehow pushes the layer interaction and leads to a more coherent behavior during the training. This is basically a trick, a kind of a trick we developed exploiting the third characteristic I discussed before. We wanted to enhance the efficiency of the learning process, and so we exploited the sequential refinement of the learning procedure, the fact that first layers of an architecture will be optimized sooner with respect to the later layers of the same architecture from the forward-forward. And we did this by assigning to each layer a probability to be trained drawn from a chi-square distribution. And so the generic block in this framework will undergo the optimization process according to a probability given by the probabilities of its constitutive blocks, of its constitutive layers, sorry. In this scenario, we also observed the loss function of the first of the trainable blocks, and if it reaches a steady state, if it reaches a plateau, the parameter phi of the chi-square distribution is incremented in such a way we redistribute the probabilities in favor of the later layers of the architecture. Of course, all this after an initial global training of the network. And we found out that while this trick somehow does not impact very much the convergence, it impacts the computational times. we wanted to produce a more efficient learning procedure with respect to the forward. So we evaluated the computational times per epoch. On the right, we can see what happens without the random training. And we can see here that the frequency of the random reorganization does not impact the computational times, while the number of the blocks does. But this is quite obvious since we know that the backpropagation is very efficient also from a computational point of view. So the more the layers in a block, the less the computational time somehow. On the right, we can see that in both the situations, the random training further reduces this quantity, almost halving the computational time per epoch with respect to the pure forward. So we developed basically a strategy that makes this learning process even more efficient and so somehow widely usable in a real context, not only in experimental ones. And given the good results of the locally backpropagated forward, we tried also to develop some applications based on its fundamental ideas, in particular in the field of federated learning. What is federated learning briefly? We know that conventional AI models are typically trained on single data set located on a single machine, and this requires the data to be aggregated. But it is not always possible to centralize data, and reasons can vary from legal to confidential. So the federated learning is an approach, is a paradigm where multiple entities called clients collaborate in solving a machine learning problem under the orchestration of a central server, and all this while keeping their dataset localized. So this paradigm shifts the traditional centralized model training to a more distributed approach, which preserves data privacy and allows to adhere to legal and confidentiality constraints. And of course, these decentralized approaches are interesting in a plethora of fields, but in particular where the privacy is a strict constraint, for example, in fields like healthcare or military research, but it also pushes the boundaries somehow of the distributed computation for machine and deep learning, since it allows the model training to be conducted on a large scale by distributing the computational load across multiple nodes. And this is particularly interesting in situations where extensive simulations are required, for example, climate modeling or large-scale industrial process. But how does the training of the local and the global model occur in the typical federated learning setting? In general, the server initializes the weights for a global model in a random way, delivers these weights to the clients that perform some local training on their datasets, and then send back the information about weights updates to the server that aggregates this information and updates the global model. And this can be done, the exchange of information about the weights update can be done by transmitting the gradients or transmitting the weights in each training epoch for the local clients, as for example in FedSGD, or waiting for some learning on the clients and then sending back these weights as in FedAVG. And it's important to notice that this second approach is usually preferred since it reduces the communication frequency and so the load for the communication channel. Of course, this paradigm comes with its own set of challenges, and among them, probably one of the most important one concerned the non-IDness of data, which basically refers to different data distributions across the clients. This can manifest in several forms that I briefly reported here, but probably the most common one is the label distribution skew, in which there is a very different distributions, there are very different distributions of the label across the various clients. And addressing this set of challenges, these issues is important, since these issues may lead to inconsistent model updates and degraded global performances of the model. In particular, a well-known issue related to the non-idealness is the model divergence, which consists basically in local models becoming very different from each others. And this causes a problem when the server aggregates these models in order to obtain the global model. Moreover, over multiple communication rounds, these discrepancies may accumulate, so causing the global model to diverge, and of course negatively impacting the performances of the whole training process. Another important challenge in this field is what we call device heterogeneity, which refers to different hardware capabilities among the clients. We know that in typical federated learning paradigms, uniform model structures are required across clients, but this may limit the full utilization of the computational power. We can think, for example, a client that is less capable, it is less powerful than the others, which may become a straggler, slowing down the entire training procedure. Moreover, device heterogeneity may also introduce uncertainty and instability, since, for example, a device with a limited storage capability may struggle in handling large model updates, so causing it to drop out of the training procedure or send incomplete updates. Of course, several solutions have been proposed to face these two challenges, and in particular, on one side, as a concern non-idealness, usually techniques involve the introduction of some regularization terms, which forces the weights to not diverge, or in weighting terms related to data distributions. As concerns device heterogeneity, some strategies rely on client selection, but this may introduce biases if not all the clients equally participate to the training process, or on split learning, which raise privacy concerns due to the communication of the gradients information. So in this scenario, and in particular, in order to address the challenge of the data heterogeneity, we exploited the idea of splitting a neural network in blocks from the locally backpropagated forward in the context of federated learning. This strategy allows us to train different pieces of a global model on different clients according to some rule, which, for example, can depend on the computational capabilities of the client. And this is what is briefly described in this slide. We basically imagine that each client receives a partial replica of the global model, consisting in a subset of the blocks in which the global model is split, perform the training on these blocks, and then send the weights to the server that aggregates these weights in order to obtain the global model. And this here is reported for this operation here is described as, for example, an average, a simple average, but this is not a strict constraint in the sense that here we can use all the aggregation techniques from the federated learning field, and this makes this technique, this approach, widely usable. In this context, of course, we must recall two important facts. That is to say that the output of the generic block also serves as input for the subsequent block. We are in a feed-forward context, and that the optimization of the generic block is somehow aware of what's happening before in the network, but not in the subsequent parts of the same network. And this implies that the partial replicas of the global model delivered to the clients must start from its first block. And this means that according, of course, to the settings of the of the federated learning procedure, but there's the possibility that the last blocks of the global model could remain untrained. So in order to overcome this issue, we exploited the sequential refinement of the learning by observing the difference for each generic communication round, the difference between the weights of the trained local model, the weights of a block, of course, of a trained local model, and the weights of the global model referred to that block at the previous communication round, which is basically the quantity I've reported in this slide. And if this quantity approaches to zero for the majority of the clients, this block is frozen, is excluded from the training, and the structures of the partial replicas of the global models delivered to the clients are modified accordingly, as reported in this blue box, basically. And this is important if we consider that in this way, all the blocks of the global model will be trained by all the clients involved in this procedure. And this is of primary importance since we talked before about the non-ediness of data. So considering that each client has its own data set, which may be different from the data sets of the other clients. And this is basically a graphical representation of what I just said. We can see that in the first communication round, the server delivers to the model, to the client, the partial replicas of the model. At some point in the training, if the first block reaches a steady state from a training point of view, it is frozen, it is blocked, and the structure of the partial models is modified, adding another block. What's important to notice here is that even if the first block, although frozen, is still delivered to the clients because it is needed for the feed-forward learning, since there is no ongoing optimization on this block, it will not require intensive computational resources. And the methodology outlined so far has been tested using parallel training among multiple clients, in particular 10, using as aggregation techniques, both FedAVG and FedProx. We are benchmarking our method, so we are using techniques well known in the field of federated learning. And we also simulated the effect of non-ediness of data through a Dirichlet distribution whose parameter beta basically represent the level of skewness in the data. The smaller mark has to be done here. Usually in real non-eddy scenarios, typical values of beta spans the interval 0.51. In this case, we also tested beta 0.3 and 0.1 in order to find out how our algorithm perform also in some sort of extreme scenarios. And these are basically the results we obtained as beta varies. We can see compared also with the IID case. In this case, we can see that performances are good and consistent unless beta becomes 0.1, where a drop in the accuracy can be observed. But it is somehow expected since 0.1 means very different distributions of data, and so the risk of model divergence, as I discussed before. What is not reported here, but it is important, is that these results are in line with the ones that can be found in literature, meaning that this idea of splitting the neural network in blocks and then training the blocks on different clients actually works and reaches the same levels of accuracy of other more standard strategies. We also conducted some experiments involving the number of the clients. In particular, we fixed beta to 0.5, and we let the number of clients vary between 5 and 50. And in this case, we can observe more or less the same, in the sense that for a reasonable number of clients from 5 to 20, the performances are quite good. there is a drop in the accuracies for 50 clients, but since we are considering beta equal 0.5 on 50 clients, means that few labels somehow in quantity will be on the local data sets of the clients. So also in this case, we are falling in a weakness of the federated learning process somehow. And finally, we tested the behavior of this approach as the number of blocks assigned to each client is varied. And we compared these results with the case of homogeneous federated learning, in which all the clients train all the blocks. In this case, we can see that this measure, these tests are used as proxy for measuring the behavior of our approach. In the case, for example, all the clients have a very small computational power. And in this case, we can see that in the scenarios A and B, basically when some clients train all the blocks or a high number of blocks, the performances are very good. We can notice a small drop in the performances where all the clients only train a small number of blocks, but also this is somehow expected, since in the procedure that trains blocks, then freeze the first block, add one more block to the training process, probably some sort of information is loose across this process, and that's why the performances are a little worse. But in any case, in line with what we saw before, and also with the case of homogeneous federated learning. And this basically concludes this presentation. Just a small remark about the two experiments, somehow the locally backpropagated, the two approaches proposed, the locally backpropagated forward forward and shallow here. Of course, they are experimental setups. We needed to understand if these approaches can actually work. And so we tested only in the case of a classification task involving two simple datasets, MNIST and Passion MNIST, only on feed-forward architectures. Of course, now on experiments will be extended on different architectures, different tasks involving more realistic datasets. And this is a brief list of the references I used for this talk. And that's it. I would like to thank you for your attention.
Thank you. Thank you so much for the wonderful talk, Fabio. Let's have a Q&A sessions. If anyone has questions, please unmute yourself and ask questions. Have you applied this method to any other data set?
No. As I said, just in the end of the presentation, these were preliminary investigations. We wanted to understand if this kind of a hybrid methodologies between the forward and backpropagation can actually work on an experimental setting. So we taken out all the possible difficulties coming from different datasets, maybe more realistic datasets or strange neural architectures. Now we know that this kind of hybrid approaches can be used. Of course, they are not usable on all the domains, on all the networks, but they have potentialities, in my opinion. And so we will deepen the investigations about their possible usage and the limitations they have somehow.
Yeah, well, although you haven't applied that other than MNIST. MNIST is like, basically 2D data, right?
Sorry, I didn't get your question. We use the MNIST and Fashion MNIST, which is pretty similar to MNIST.
So that's basically two-dimensional data, image data, right?
Yeah, exactly. They are basically in both the cases, so they are two-dimensional data.
Right.
We didn't try it with three-dimensional data like CIFAR-10, for example. We didn't actually. We conducted some experiments, for example, on CIFAR, but we noticed that feed-forward networks struggle in reconstructing patterns of CIFAR due to the high dimensionality of the data. So we should better investigate this aspect, or try the application of this kind of learning strategies on other types of layers, for example, convolutional networks, in this case, convolutional layers in this case.
I see. I see. Any like expectations you have based on the experience on this two-dimensional analysis?
Okay,
When
actually,
you go to the 3D data?
yeah, I actually, after we worked on this in literature, have emerged some other manipulation of the forward forward algorithm, which basically rely on the approach we had, that is to say, improve the collaboration of the layers. This is probably the main weakness of this algorithm, and this is what it has to be pushed to widen the range of the applicability of this algorithm. All this to say, I think that someone has tested this algorithm on CNNs by applying a two-step backpropagation, alternate backpropagation. I don't exactly remember the name of the paper, but it is a very interesting work. So I think that these approaches can be extended to at least two different architectures.
Okay. Thank you. Is there any other question from audience? If you do, please unmute and then ask questions. If not, well, let's thank our speaker, Fabio, for the wonderful talk. And hopefully through this talk, there will be some collaboration between Fabio and some folks at the Lawrence Livermore National Lab, or any other folks from the outside. Thank you, Fabio.
Thank you very much, and thank you again for this opportunity. Have